Now we're going to consider floating. So we're going to be looking at the square boat, rectangular boat, sorry. So the rectangular boat, it's considered an open box boat. It's got a width of W, it's got a length of L. You're going to put it in the water. This is water here. And it's going to sink a little bit, and it's going to sink to some depth D, where the bottom of the boat is depth D below the surface of the water. And it's going to float at a position where the net forces in Z are equal to 0. So we're going to calculate the position where those net forces will be equal to 0, and that will tell us how deep the boat will sink until it starts floating. Or obviously, if it goes too high, it sinks too much, it will sink. Anyway, so let's calculate our forces. So we know the forces. The force on the bottom of the boat is caused by the pressure of the water acting on the bottom of the boat. And we can now calculate the pressure on the bottom of the boat. The pressure on the bottom of the boat is going to be the atmospheric pressure plus the density of water times G times D, because that's the pressure at the depth D below the surface of the water. And that's going to act on the boat's bottom, which has an area of LW. So that's going to give you a force pushing upward, because pressure always acts normal to the surface. So from the bottom of the boat, it's going to push upward on the boat with that force. And we're going to have a downward pressure, which comes from the air. So the air inside the boat has atmospheric pressure. That's going to push down on the bottom of the boat. But it's going to be atmospheric pressure plus a small correction, because the air at the bottom of the boat is actually a little bit deeper than just the surface of the water. So P naught is the pressure of the atmosphere right at sea level, or right at the surface of the water. So the pressure right on the top of the bottom of the boat from the top side is that P0 plus rho air times GD. And of course, that pressure is also acting on the same surface area of LW, and that's going to be pushing down. The atmosphere is pushing the boat down into the water. And the final force is the gravitational force, the mass of the boat times gravity. So we have the mass of the boat times gravity. Of course, gravity is trying to pull the boat downward. We're going to break those forces out so we can see them a little better, break these terms apart. So we have P naught LW plus rho of water times GD LW minus P naught LW again minus rho air GD LW, and then minus M boat times G. Obviously, these two terms cancel, and these two terms look a lot alike. They both have GDLW, so we're going to rewrite those, make them look pretty. So we've got GDLW times rho water minus rho air, and then finally we just have this gravitational term, M boat G. Notice we have G, now for this thing to float, we said that Fz has to be equal to 0. So that's 0 on the left when it's actually floating, just sitting there still, not going up or down. So we have GdLW equals rho water minus rho air minus M boat times G. Both terms have G, so we can divide by G and get rid of G, which is interesting. Gravity doesn't matter. It affects both terms equally. So then we have that the mass of the boat is going to equal, and pull that over to the left, LWD times rho of the water minus rho of the air. So that is the first result we get, which is that the mass of this boat can be calculated is related in these ways. And notice that this grouping right here, LWD, that's the volume of water displaced by the boat. So water displaced by the boat. So the boat has a length of L, a width of W, and it sinks amount D into the water. So that's the total amount of water pushed out of the way by the boat. So that total volume of water displaced times the difference in densities gives me the mass that is supported there in a floating situation. Finally, I can rewrite all of that into D. So I have D equals, the mass of the boat divided by rho water minus rho air times L and W. So that's pretty simple. So that's my formula But there's another step we can do here because we know the rho of water. The rho of water is about 1,000 kilograms per meter cubed. In fact, that's very, very close to it at most conditions that we study. And the rho of air is very different. It's 1.2 kilograms per meter cubed. Now that's, it does vary with condition quite a bit, so it could change. But you notice that it's about 1,000 times less. It's about 1,000 times less. We've talked about this before. So rho water minus rho air, it's really just approximately rho water. That's subtracting 1 off 1,000. That's less than a % difference. We can almost always ignore that. So we can rewrite this formula to make it an approximate but highly accurate formula. But the depth at which the boat is going to float is the mass of the boat divided by rho water times simply LWD. Oh, sorry, LW. Good. All right, so LW. So that's that. Now, this final thing, we're going to consider an object that is completely submerged in water. So for an object completely submerged in water, if it's filled with air, we know that the buoyancy force will be the volume of the object times G times rho water minus rho air. So that's the formula we already came up with. It's going to be the total volume times gravity times the difference in density between the water and the air. But we can, again, assume that the air density is much, much less than the water density. So this is a formula you see a lot. It's the upward buoyancy force is the volume of the object times G times the rho of that water. So that's what you see as a typical calculation of buoyancy for an object that is full of air and is completely submerged in water. So if it's full of air and completely submerged in water, the buoyancy force is the volume of the object times gravity times the density of water.